League of Women Voters Forum, Line 5 and Other Challenges Impacting the Great Lakes.
Okay, well, thanks for coming out. I'm Eric Anderson, as Terry said. I work for NOAA's Great Lakes Environmental Research Lab, so it's actually located right here in Ann Arbor, about 3 miles south on State Street. Although we've moved around for several years, we've been here since 1976 or 74, I believe. So right after NOAA started, they opened a branch here in the Great Lakes. So today I'm going to talk about some of the work that I do, kind of focused around forecasting of mostly currents in the Great Lakes, because those have impacts really close to some of the issues that are hot topics right now in the Great Lakes. So things like oil spill response related to a lot of questions we have about the Straits of Mackinac, as well as things like algal blooms or even Lake Erie's dead zone. So I'll touch on those topics a little bit too. And if anybody can't hear, just raise a hand. I might be rotating a lot, so hopefully I won't pull away from this mic too much. So let me give a little background on NOAA first. So NOAA, if you're not familiar, is the National Oceanic and Atmospheric Administration. As far as federal agencies go, NOAA is essentially supposed to be the public's eyes and ears for all things environment, okay? So we are trying to figure out what's going on right now related to the environment, atmospheric, oceanic, and those include things like the biology, the ecosystem that's out there. What makes NOAA unique, though, is not just that environmental intelligence, which is kind of what a previous director has referred to it as, but NOAA is unique through forecasting. So NOAA tries to not only tell us what's going on right now, but what will happen next hour, or in a week, or in a month, or even multiple years out from right now, related to these various issues. So to do that, NOAA uses basically several different what we call line offices. The one you're probably most familiar with is the National Weather Service. It's where we get our weather information from. If you don't think you get your weather from the National Weather Service, probably 100% of it, or a pretty large majority of it, does get fed into whatever means you get your weather from. So if you go to the Weather Channel, for the most part, they're repackaging NOAA data, NOAA models, and putting that up in maybe a better format that you like better. Or even if you're using something like AccuWeather, they're running their own weather models that use, by and large, data information, NOAA data and NOAA model output to produce those weather forecasts. But beyond weather, NOAA does a number of other things related to that. So they also do ocean forecasting through the National Ocean Service. And this is more related to what I do. And it's not prediction of what's going on the air side, it's prediction of what's happening on the ocean side. So things like currents and waves and water temperature and ice. There's also the Fisheries Service, which doesn't have jurisdiction in the Great Lakes, but they would do things like regulate and manage the fisheries out in the ocean. And there's the satellite service, which is providing you this image from right here. This is the new GOES satellite that launched last year. There's some overlays there outlining the borders of the countries, but otherwise this is a true color image from a geostationary satellite that NOAA and NASA put up to give us a real-time, essentially, view, constant, of this part of the world. And you can see here, this is actually, I grabbed this for a talk I did in September. You can see the hurricane, I think this is Irma, moving through the Gulf of Mexico there over Texas. So my role in that is not looking at this global view, but looking at this view. What is going on in the Great Lakes from an environmental standpoint, and what will happen, again, on these different forecast horizons, 5 hours from now, 5 days from now, 5 months from now, things like that. However, at our lab, we're primarily focused on the water side. So we're not doing the atmospheric, the weather side that, again, most people are familiar with NOAA for. We're doing the water side, what's actually going on in the bodies of water in those lakes, as well as the water that exists on the land. So we call this hydrology, right? The runoff from the tributaries, the streams, things like that. So we're looking at maybe all things water and the stuff that lives in the water, although I don't do the biology stuff, so I will steer clear of that today. But historically, this has been things like supporting commercial navigation. That's really, from the water side, where we got our start. On the atmospheric side, of course, they're doing support for the airline industry, right? Trying to fly safely, getting from point A to point B. It's the same on the ocean side. So essentially, when a ship leaves Duluth, say bound for Cleveland, like we are in this case, information on what these waves are going to be that they pass through Superior and Huron and Lake Erie, what those are going to look like, not only now again, but over the next few days as they try to traverse that distance. as well as things like ice. Are they going to come across ice in that path? What is the water level going to be? How much cargo can they load in that ship in order to get through the St. Clair River, which is the bottleneck as far as depth is concerned for the Great Lakes? So this kind of information has been the bread and butter for NOAA for several decades. Before we had these kind of forecasts, for wave forecasts, we had tragedies like this, right? So the record of Evan Fitzgerald from 1975, came before we had this type of forecasting, modeling information that we do today. So back then, a lot of information on what the wave heights were based on a couple of buoys that were out there that didn't transmit data very well, and then ship reports. So as the Arthur Anderson and as the Edmund Fitzgerald drove through Superior, they were basically calling in wave heights as they came across them. And they didn't have this picture of what the waves were at that time. Otherwise, they probably wouldn't have gone into basically the worst spot at the worst time during that event. Now, since then, we've moved on beyond just this support of commercial navigation to other things like protection of drinking water, response to oil spills. So when an oil spill happens, the kind of stuff that I produce at our lab, which is, again, forecasting things like currents, or what we call hydrodynamics, which is really trying to forecast all things physical of the lake. So again, waves and currents and temperatures. In the event of an oil spill, the currents that come out of these models, the forecasted or predicted currents, will be used to tell oil spill responders, like the U.S. Coast Guard or the EPA, where we expect that oil to move, and they can come up with a plan about how best to respond, where to protect, how to contain that oil, and other options that they might have. Beyond that, we also do things like support drinking water intakes. A classic case going on right now is in Lake Erie, protecting those drinking water intakes from things like harmful algal blooms. So in the Great Lakes, we drink our water, right? Different than the ocean coasts. So when this algal bloom forms in Lake Erie and it gets anywhere near those intakes, we have something to worry about. And if you're familiar with the 2014 event in Toledo, where they had to shut down drinking water for about 500,000 people when toxic water from an algae bloom got into the intake, into the water supply, that's the kind of stuff that we're kind of forecast, I wouldn't say against, but give people information that they need to make decisions before it's too late. And so I'll talk a little bit about these two processes and also something called hypoxia, which is the dead zone in Lake Erie, right at the end. So for me to do my job, to forecast currents in the Great Lakes, it really all starts with what the meteorology is over the lake. So what is the wind doing over the water? What is the air temperature? What's the cloud cover over the lakes? These things all sound like they might not be that hard to do. It's 2018 now. We have a number of things to be able to look at the Earth. We have satellites in space pointing down all the time. We have observations all over. We have fast computers to be able to model these things. But it's a pretty difficult process to know what's going on out in the middle of Lake Superior compared to what's going on, say, right here in Ann Arbor, right? And I'll get into a little bit why that is. But it all starts with this. So the currents in the lakes are pretty much driven by what you're seeing right here, which is the wind field over the Great Lakes. That's the big driver. We don't have really tides to speak of. We have very small tides, about that big. So that's not really what's driving a lot of stuff going on as far as currents goes. It really all starts with wind. And as that wind moves over the water, it grabs that surface layer of water and pulls it along with it. So you can see here an animation in the top right of surface currents in the Great Lakes from a snapshot that I took. And you can see those lines moving across the surface. That's basically the direction of the wind as it rode over that piece. It grabbed that water and pulled it along with it. And then this bottom left plot is the currents basically below the surface, out of the reach of the wind, but they end up moving in a slightly different way most of the time to compensate for that flow that's happening at the surface. So at the surface, you can have currents going one direction and subsurface in a completely different direction. And you see some of the neat gyres that show up in the Great Lakes. You can see here, if you're close to the front, I apologize if you're in the back, but the gyres are set up like in Lake Erie, this big gyre in the Central Basin that controls some of that stuff like we saw with the harmful algal blooms. So we have a general understanding of circulation patterns in the Great Lakes. This is a snapshot of summer circulation. So the circulation patterns kind of change by season, but it's essentially kind of a summer-winter situation. Where we have general ideas of how flow moves, how water moves in the system, but over very long time scales. So think like more like geologic time, maybe multiple years or decades, or at best seasons, right? So this gives us an idea of how things work in the Great Lakes from that time point. But really, at any given time, the currents in the Great Lakes do not look like this. In fact, it's probably a certainty that they will never look like this in the Great Lakes at any given time because they're wind-driven. So we know the wind changes every few minutes or hours out there, right? And it can change from one direction, completely the opposite direction, from basically no wind to dead calm to whipping up over a storm as, say, a thunderstorm moves in. And with that, the currents respond just as quick. So we really never had this nice clean picture of circulation out there. We have something much more dynamic that changes at the speed of the wind. So if we want to predict what's going on current-wise in the Great Lakes, we can't rely on those circulation maps or those observations that we made maybe 30 years ago. We have to have up-to-date information. So this is thinking about what's going on right now. Again, thinking NOAA's focus is what's happening now and what will happen in the future. We start with the now. What is going on? We don't just start with the Great Lakes like we did maybe in 1970 by using observations that we had at, say, a nearby airport. We're thinking now from a global view. So we have these satellites in place. We have observations all around the globe, and we have computer models of the entire globe that produce things like this, which is a wind field. This is a snapshot of a global wind field from NOAA. It gives us an idea of what's going on around the world right now, our best understanding of what's going on. And then we can use things to forecast what's going to happen in the future, pretty much all driven by the sun, right? So the sun heats up different parts of the world as the Earth spins around, and that causes our weather, right? So we have pretty good understanding of what drives the future. The difficult part is really knowing what's going on right now. It's very hard to figure out all the information we have, especially in points, say, out in the middle of the ocean where we have very few observations. But this is where it starts. So we have a wind field for the globe, and I'm going to say a lot of things about wind field, but really it's all pieces of meteorology, and I'll get into a few of those in a second. And for us, we scale this down to the Great Lakes. So what is that global weather situation doing for us right here in the Great Lakes? If you were here a couple weeks ago and we had that extremely cold snap that was driven by essentially cold air coming down from Canada from the Arctic, that's the kind of information we're looking for. So we can't just think about these borders. We have to think about what's going on outside of our region as well. So we take this weather information, again, predicted maybe or simulated by a model, but we're always trying to tie it back to reality. So in the Great Lakes, we tie this to a number of observations that we have through really around the region. I'm just showing here the ones close to the lakes themselves. There's several measurements inland, of course. This map would be pretty solid with measurements or observations on the land. But on the water, we're focusing on the coastal stations that are out there and a few spots over the water. This gives us that information that we can use to steer those models to say what's going on, say, as far as the wind or clouds or air temperature over the water itself. Now, quite a few of observations. Actually, if I show this to, say, ocean colleagues, they're pretty much drooling when they see this picture. Look how you have so many observations. We have nothing, if you're trying to model, say, the mid-Atlantic. But I'll show you something else. This is the number of over-water observations that we have at best. So this map, this is primarily a map of the buoys that we have in the Great Lakes. It's kind of an evolving picture. So 20 years ago, there was maybe 2 points per lake. We have quite a wealth of data right now. I should say right now. I don't mean actually literally right now. This is the picture right now. Why is that? It's winter, right? All the buoys come out of the water before the ice comes on. So right now, it's much harder for the models to be steered by reality, so to speak, to be, I shouldn't say steered, but anchored to reality than it is in the summertime when you have a picture like this. So it's always a difficult job to understand what's going on over the lakes. But the information that comes out of those weather models, things like, again, wind, air temperature, dew point, cloud cover, a whole slew of things, precipitation, things like that as well. Those are what drive my models. This is really where my job starts. Just like you, I'm getting this weather information from some forecaster, some model that gives me an idea of what's going on now and over the next few days, and that's what I use to drive my models of the Great Lakes. So what this is called, the models that we run, that we develop here in town, are called the Great Lakes Operational Forecast System. Long word. Really just refers to a set of computer models that represent the lakes, basically one per lake. We call these real-time hydrodynamic models because they run every few hours and produce a picture of what's going on right now. We call that a nowcast. You probably don't see that on the local news, but then it also kicks off a 5-day forecast. People are more familiar with that word. But again, both of those parts are critical to understand, again, how to respond now and in the future to whatever events might be concerning. The kind of stuff that comes out of this is what I've been talking about: currents, water temperatures, waves, water level fluctuations, things like ice as well. So any physical part of the ecosystem, of the environment, is being predicted by these models. And then these can inform things like ecological models that might model how an algal bloom grows or even how fish respond to certain conditions. So these models are basically broken up into several little triangles of various size. And if you can see these from where you're sitting, there's bigger triangles out here. This is the Straits of Mackinac, of course. Big triangles out here in the middle of northern Lake Michigan. So small that you can't really even see them in the Straits of Mackinac. So we have basically this variant we call a grid or a mesh, a computer mesh that is our model. And what these are is in each triangle we can make a prediction of what that physical attribute is. So if it's a current, I can tell you what the current is, or I can try to tell you what a current is in each one of these triangles. So a triangle out here is much bigger, maybe the size of about a mile. In the Straits of Mackinac, we can make those predictions about the size of a football field, so every 100 meters or so. And we make those triangles bend to how complex that situation is. So we need more information here in the Straits to predict what's going on than we do, say, in the middle of the offshore region of the lakes. And with this computer model, we get predictions like this. So this is a snapshot of the currents in the in the Straits of Mackinac. You can see surface currents here, and I'll get into in a little bit what's going on here, why they're oscillating and moving around so much. If people were here for a talk by my colleague Dave Schwab last year, he got into this a little bit, and so hopefully I'll expand on that without being too redundant. But this is the kind of information we get out of our computer models. And it's not just in areas like this. We get it for basically any region of the Great Lakes. So here's a surface current map for Michigan and Huron. Again, really, they're one lake, so they're connected to the Straits of Mackinac. A lot of people maybe aren't aware that it's the largest lake in the world by surface area. But it's a massive lake and a lot of dynamic stuff going on in the system. So we have surface current maps, again, all kinds of physical conditions, surface temperatures as well. And just like we do on the weather side, we're always trying to ground truth this or compare this to reality to make sure that we're on track. So we have a network of observations. In this case, again, our buoy map, again, for the most part, some coastal stations where we have water temperature, in this case, being measured. But again, all the things that we're predicting, we have measurements of that we're trying to compare to. We grab those observations, compare them to the model, and see how well we do. So this is a good example of us predicting surface water temperature out in the middle of Lake Michigan here, so kind of offshore of Chicago and Milwaukee. Our error in the model, this is for last year, was less than a degree, so 0.75 degrees Celsius, which is really good. It's not always so good. I picked a good one to show you. But again, it all starts with the weather. The more accurate the weather is, the better we are at predicting how that water responds. And all this information then comes out on our page. So we have, this is our site that we run here in town. Again, we're called the Great Lakes Environmental Research Lab, or for short, GLERL. So if you hear me say GLERL, which is a weird word, that's what I'm talking about. It's our lab. So that information comes out. This is a real-time page. So again, updated every few hours. You can get information here, but this information is also grabbed and put out by channels like the Weather Channel and those kinds of information. Or if you get a marine forecast for the lakes, those weather forecasters, whether they're weather service forecasters or other types of forecasters, are getting information from this. Most recently in the news, and maybe most relevant to thinking about the Straits of Mackinac, Enbridge is watching wave predictions in the Straits of Mackinac that comes out of these models. And I can answer questions about that later if you have them. So this system is what we then use to try to give information in the event of, say, an oil spill, or in the event of we need to protect drinking water, or things like that. Or even things like search and rescue. When the Coast Guard has to go find somebody in the lakes, these are the currents they use to figure out where they might be if it's not known. So I'll talk a little bit about the Straits of Mackinac first, and how my work relates to, say, oil spill response in this system. So again, Straits are a very dynamic zone. I think when Dave was here, and you've probably heard this other places, the Straits of Mackinac, some say, is the most dynamic spot in the Great Lakes. And I can't really argue against that. It might not be the most, but it's certainly one of the most dynamic places in the Great Lakes. And I'll get into a little bit of a reason why. Now, as far back as probably people have lived here, the Native Americans have been here, they've experienced that crazy nature in the Straits. The first writings that I could find about it are from a French explorer in the late 1600s. He sailed through the Great Lakes looking for the Mississippi River. When he got back, he wrote a book called Voyages to the New World, and in it, he actually referenced the Straits of Mackinac. And so I'll read this to you in case you're far in the back, but he talks about how wild the Straits are. So, in some seasons, it so falls out that the currents run 3 days eastward, 2 to the west, 1 to the south, 4 northward, sometimes more, sometimes less. The cause of this diversity of currents could never be fathomed, for in a calm, they'll run in the space of one day to all points of the compass, sometimes one way, sometimes another, without any limitation of time, so that the decision of this matter must be left to the disciples of Copernicus. Basically, I'm a sailor, I don't know what's going on in the Straits of Mackinac, let the scientists figure it out, right? That's basically what he said a long time ago. And we, as a scientific community, really didn't make much progress for about 300 years on what was going on in the Straits. Our lab in 1976 made some measurements in the Straits with some very early current measuring devices, and measured this big fluctuation in currents going on in the Straits. And you can see this plot here. That's just to give you an idea of just the relative change in current speed in the Straits of Mackinac itself. Another important point they found was that there's also a difference in the currents you see at the surface and subsurface. Now, I talked about that a little bit, but the unique thing here is in the Straits, in the summertime, when you have warm water, relatively warm water on the surface, and it's very cold down below, say 80 meters down, those currents go in different directions a lot of the time. So the surface can be going from Michigan to Huron, subsurface is just the other way. And so they measured this phenomenon, and they were like, well, the currents are fast, they change all the time, and in the summer, things are even crazier than that. So they really kind of proved the French explorer's point that he made 300 years before. Now, it wasn't until essentially a few years ago that my colleague and I made the first computer model that included the Straits of Mackinac that could resolve some of this information and give us some insight into what's going on up there. So we now have a more full picture of what's happening in the Straits of Mackinac, and as I get to in a second, what's really driving the flow there. So again, you see this is a plot of that flow going back and forth through the Straits of Mackinac. Things basically on the top side here going into Huron, and then when you see the fluctuations go below the center line, it's going back into Michigan. So this is a plot basically for most of the part of the year. You can see it oscillating back and forth with a huge volume. So to give you an idea, the volume there going back and forth just in a couple of days, that amount of volume would be enough to drain Lake St. Clair. In fact, Lake St. Clair would drain probably in less than a day. That amount of volume flux would drain Chesapeake Bay in about 7 days. So it's a lot of flow moving back and forth between there. Even though the net flow is from Michigan to Huron, it's pretty small. The big fluctuation that you see every other day is at a much larger scale. And you can see an example here. This is a computer model we have of the Straits. You can see the currents going back and forth. You don't get an idea of speed there, but the currents can get up to about 1 meter per second, so 3 feet per second. That's what you would see in a river. Picture Niagara Falls and the water rushing over the edge. That's kind of the speed you're talking about here. Much faster than you see in most places in the lakes. And again, this bottom to top difference in current direction, this animation I think will play through the whole year, so we may not see it, but in the summertime you can see the surface goes, here we go, it's a different direction than you see in the subsurface. That makes things tricky, I think, especially if we're thinking about how, say, a contaminant that might be released at the bottom or top might act differently than at another depth. So, flow in the Straits. We've measured it several times in the 70s, again in the 90s, and then the last 5 years in a row we've been measuring currents in the Straits to support this modeling endeavor that we're going through. Generally, the oscillations that we see occur all year long, so this fluctuation really exists all year, and it's pretty consistent. It oscillates on a pretty regular 3-day period, so that means the flow will go into Huron for about a day and a half, go back into Michigan for a day and a half, and then start the cycle over again. And that really exists all the time, and we didn't know why. A few years ago, we didn't have a good understanding of why that was. Even if the wind was dead calm out there, what's causing this fluctuation? Well, we came across, again, a combination of measurements and models and started to dig away at this answer, and we realized it was something called Helmholtz resonance. And I won't bore you with the details, but I will say that you already know what this is. So Helmholtz resonance is something that we're all familiar with. It's the same phenomenon that happens when you blow over a jug. So if we have any jug band players here, you fill up your jug with a little bit of water and you blow over it, what happens? Sound comes out, right? So that's what's going on with the Straits of Mackinac, and I'll show you why. So when you blow over a jug, air goes down into the jug, the pressure increases, that pushes the air back out. You get some vibration between the air going in and out, and that's the sound you hear, right? That vibration, fluctuations in pressures, creates a pitch. That's what's going on in the lakes as well. Essentially, you have air going, or in this case, water going back and forth between the two lakes. Give a certain frequency that's dependent on how big that jug is, how full of water it is. And you get a certain, in the jug case, a pitch. In the Great Lakes, what that ends up being is basically a fluctuation, a period of how quick that fluctuates. And so what this looks like in the lakes is as a weather system moves across one of the lakes, again, this is the air being blown over the jug, pushes, in this case, pushes water down in Lake Michigan. It shoots through the straits, raising the water level in Lake Huron. As that storm system passes, then the water goes back down on Huron, shoots through the straits, and goes back up into Michigan. So that's that oscillation through your jug bottleneck, right? The bottleneck is the Straits of Mackinac itself. In this case, you have two jugs, a Huron jug and a Michigan jug. So that analogy breaks down a little bit there. But essentially, that's what's going on. What that means is that a weather system moving over any part of Michigan Huron affects the flow at the straits. So you can have no wind. It can be a dead calm at the Straits of Mackinac. It can be covered in ice, which it sometimes is. And you can have a storm blow over, say, Chicago, and it'll set off this oscillation in the Straits of Mackinac. And that's why it's going all year round, all the time, because there's always some kind of wind blowing over some part of that lake, right? In fact, over most of the lake all the time. But even when you see calm conditions up here, if there's something moving over, say, Saginaw Bay, it's kicking off that oscillation. And because we know the jug, the frequency that you hear, the pitch you hear in the jug is depending on how big that jug is or how full it is, we can do the same thing for the lakes. So we know how big the lakes are, how full of water they are. And we know the size of the Straits of Mackinac. We can use that same mathematics to calculate what that period of oscillation should be. And it's just about 3 days. So it's pretty much what we measure. This is the driving force of what's going on in the straits, and also why it makes it so difficult to figure out why the currents are what they're doing when you're in the straits, sailing through them to figure out what's causing those changes in currents. All right, so not only have we measured it with current meters, and that's what those devices that I showed in the 70s were called, and modeled it with computers, we've also done things like deployed drifter buoys in the Straits of Mackinac. And so what these are, just very simple Home Depot built things with a GPS tracker slapped on top. We can throw this into the water, and they track the current. So it gives us a moving picture of what those currents are. It's pushed around, just like if a person was in the water, right? How that would move around. Not exactly like how oil would move around, because this thing's, of course, looks like a kite. It's much bigger than an oil slick, but it's still tracking those currents. And it's a nice way to visualize what's going on in something like the Strait. So what you'll see in this next image is 3 drifter buoys that we released in September of 2014. We've done a whole series of these. You'll see them get dropped in the water, 2 at first, and the third will join them. The 2 will shoot to the west, and they'll get sucked back towards the straits, and you'll see this oscillation happening, which is pretty cool. So these are the drifter buoy tracks. You can see the 2 shoot out towards the west. They start to get sucked back. The red one starts, again, makes it almost to Sheboygan before it gets sucked back, and then does shoot out into Lake Huron. And again, we've done this probably 10 times. And when they don't beach, which happens in a lot of cases, they can go back and forth between that straits, make 10 to 15 passes before they eventually hit something. So pretty wild phenomenon that we see here. And what I also want to point out is, take a look at this pattern. So we oftentimes see this kind of tilted, slant to these trajectories. So when they're in Michigan, they sneak up along the UP. When they're in Huron, they kind of tend to go between Bob Lowe and Sheboygan here in Lake Huron. So remember that as we go to this next slide. Now, again, I said that's not oil. A drifter buoy is not oil. It's kind of tracking the currents as best we can. But how does something like oil or a contaminant move in the system if it was released in the straits? And why do we call this, again, one of the most dynamic spots in the Great Lakes? I'll show you why. So what I'm going to show here is a simulation of not exactly oil, but an oil-like substance. So this is what we call particle release. 2 releases I'm going to show here. One's on the surface. You'll see red dots. Those are things floating on the surface, lighter than water. And then black dots would be something that's a little heavier, that's not going to float to the surface, and it will track those subsurface currents that we talked about. So I'll show 3 releases. One in the Straits of Mackinac, one in the center of southern Lake Michigan, so Milwaukee, somewhere over here, Chicago's down here. This is dead center. And then one in western Lake Erie. And there's going to be a big difference between what the Straits looks like and what Michigan and Erie look like. So here's the releases. These are these blobs. So it's an instantaneous just dump of something. Could be oil. Right away, you see the patches in Michigan and Erie look vastly different than what you see up in the Straits. And that's because of those 3 factors. The currents are oscillating, the currents are fast, and they're different on the surface and subsurface. They're also different on the surface and subsurface in Michigan and Erie, but not as drastic, right? You can see some variation about how these are moving, but they stay together pretty well for, this is almost, this is over 5 days now, I'm getting close to 10. In the Straits of Mackinac, it's a whole different situation, right? This is already spanning several hundred, or maybe 100 kilometers at this point, stretching from, near Manistee to past Sheboygan. Let's watch that again. Again, even after a few hours, the patch in the Straits is ripped apart compared to the other two. So when you think about this from an oil spill response standpoint, if you were trying to contain or respond to that oil spill, you have a much easier, not easy, but much easier situation down here than you do in something like this, let alone the coastline, right? Out in the middle of these lakes, of course, you're away from the coastlines. And here, pretty quickly, you're going to have a coastline impacted right away. And you've seen those reports that have talked more about that kind of information. So a very different situation going on in the Straits. I'll mention, if you go to our site, you can pull up a lot of this information that I'm going to show today, or always email me after if you have further questions. So a pretty dangerous situation. That's why we call it one of the most dynamic spots in the Great Lakes. It's from a navigation standpoint to a contaminant response standpoint, it's a very unique and pretty wild place to be, and therefore needs something like we do, which is forecasting the conditions there in the Straits. And actually, if an oil spill were to happen in the Straits of Mackinac, these are the models that would provide that information, as I say, of what might happen over the next few days. So we had a spill exercise back in 2015, where a number of federal partners, state partners, tribes, even Enbridge really coordinated the whole thing, got together to basically do a spill exercise. And these are common. So the Coast Guard does these all the time, just to keep people trained up on what to do and also be ready in areas where you might have a dangerous situation. In this case, we did an exercise in the Straits, used our currents to try to tell where that oil slick would go, and then all these other agencies, these responders, use that information just like they would maybe in real life and see what problems they might have, what they might encounter. So in this case, we see a rupture. 6 hours later, we expect the slick to surface there, in this case, west of the Straits. It's all depending on timing of when it's released. Move a little bit further west over Wilderness State Park, and then start to come back through the Straits, just like we saw with those drifter buoys, and start to hit the islands there, just south of Mackinac Island, towards Sheboygan, then impacting St. Ignace, 48 hours out, 60 hours out, and so on. So again, this exercise happened in 2015, but if a spill happened today, this is the situation we would have from the NOAA side. We provide this information to the Coast Guard, to the responders, tell them where we think that oil slick's going, and give them the best information we can so that they can respond. Now, I'm going to switch gears before I end and jump on to something not all that different than oil spill response, but in this case, protecting our drinking water. So in this case, things like harmful algal blooms and, as I mentioned before, hypoxia. But these all relate, these are all driven by the same hydrodynamic models that I developed. So forecasting currents provide the same kind of information to these two efforts as we do in an oil spill response. So in this case, let's start with harmful algal blooms. I don't want to give too much of a background on these. You guys have probably seen these in the news and could be much more familiar with them than I am. But in recent years, we've had a pretty bad problem in Lake Erie related to algal blooms. Major news. I could fill up this page with national news articles talking about Lake Erie, unfortunately. One of the reasons we get involved in this, there's a whole suite of partners looking at trying to solve the algal bloom problem in Lake Erie, from management and regulation to, collecting or reducing the amount of phosphorus we put into the lake. NOAA's response to this, NOAA's place in this is, again, in this forecasting piece. So if there's an algal bloom, where's it going to go? How bad is it going to be? Do we need to protect drinking water from that bloom? So in Lake Erie, there's a number of drinking water intakes. All those yellow dots are a drinking water intake that we have for the U.S. and Canada. Again, could be impacted by both HABs, harmful algal blooms, or hypoxia. I'll start with HABs. As you might know, big problem with water quality in the Great Lakes back in the 60s and 70s. The Great Lakes Water Quality Agreement was signed in 1972, binational agreement that really cleaned up the water. So from a harmful algal bloom standpoint, we had a really great almost 2 decades out there. And then in the late 90s, early 2000s, the algal blooms came back, and they really ramped up, almost linearly. We saw things slowly creep back up, and really in the last 7 years, get significantly worse. So in 2012, we had a record-breaking year in Lake Erie. That was broken in 2015. And then in 2014, of course, we had the toxic water incident at Toledo. Down here, if you've been not listening to me and watching this is the HAB from this year, from 2017, the satellite imagery that we used to detect the HABs, and I'll get into that in a second. You can see it towards the end of the year. Here's the algal bloom starting to grow in the Western Basin, and it basically starts to fill up the Western Basin and move out into what we call the Central Basin or towards Cleveland by the end of the year. So HAB forecasting. Again, NOAA's role is very similar to what we do with weather and water and oil's response. Where is the HAB now? Where is it going to be in the future? In this case, is it going to get down to a drinking water intake, or is it going to just float on the surface and be a scum, right? Two very different situations. On the surface, charter fishermen are upset. They have to avoid this thing. Beachgoers are upset. But when it mixes down to the water column, now drinking water is impacted. And they don't know necessarily when that's going to happen. So we need this kind of information to give them some direction about how to respond. So on the where is the HAB now part, very similar to what we do with the weather side and even the oil slick side. We are out there taking measurements on at least a weekly basis, but we're working with a number of partners to take more frequent samples than that. Texting, is the bloom there? Is it toxic? We have satellite detection, so we get a few satellite passes each day. It gives us information like this in 2012, where you see the algal bloom there. So that gives us good information when it's cloud-free. What do we do when it's cloudy? The satellites don't see this kind of information. Well, recent years we do something called flyover detection. So we just hire some folks actually from the Ann Arbor airport. We strap a sensor to their plane. They fly under the clouds, and we get although small scale, we get information on how bad the HAB is and where it's at. So we get these kind of pieces of information together. We get a nice view of where the HAB is now. And now, again, from my standpoint, this is where my job starts. You told me where the HAB is. Now I'm going to tell you where it's going to go. And to do that, we again use a combination of models. So this hydrodynamic system that we call the Great Lakes Operational Forecast System. And then we also use something that we call the HAB tracker. That name started as a joke, and it's kind of stuck. But it's essentially a HAB computer model that represents what the algae does out there when it's being pushed around by these currents. So does it float towards the surface to get some sun, to get some food, basically, midday? Or does it get mixed back down to the bottom? Does it grow? Is it dying off at the end of the season? That kind of information. When we put those all together, we get, just like we would an oil slick forecast, we get a harmful algal bloom forecast. You can see here the bloom growing in late July. This is a simulation from 2016, our forecast that we made then. The rainbow colors there are the bloom, different intensities. Blue would just be, open water and no algae detected. You can see the bloom form in the Western Basin, starts to grow outward. You can see also this pulsating nature. So maybe it looks like the bloom grows and disappears. What's actually happening, again, is the wind is mixing it back down in the water column. So it's not detectable on the surface. That's also a problem when you're relying on satellites that can't see below the surface. It can seem like the bloom's gone or maybe dissipated a little bit, when in fact it's just mixed down and down towards the water intakes potentially. So this becomes a problem, and that's why we have not just a two-dimensional model, but we can look below the surface. This is a plot of, again, algae concentration as a function of depth. So these are algae on the surface where you see red blotches. Those are basically a scum forming. And in this case, if I was a drinking water manager for a plant, for the Toledo plant, I would say, okay, right now it looks like a scum is formed above my water intake, but 4 days out, it looks like things are mixing down in the water column. So if my intake's sitting on the bottom, at day 4, I better be prepared to start looking for toxic water and treating a little bit differently. Now, just like all these systems, we're always tracking how good do we do, right? We're always focused on how good are the models. If we're going to put this information out there and people are going to make decisions based on it, we have to be accurate, right? We can't have water intake shutting down drinking water for Toledo based on a bad model. So in this case, we do things like this. We compare on the left, this is the model forecast, versus on the right, satellite observations. Doesn't look like a satellite, I realize, but we're putting them on the same scale so we can make comparisons. So you see, anywhere you see gray in the satellite, that's cloud cover. So here's a very cloudy day over Lake Erie compared to a nice open day on the bottom. But what you'll see here is on day 1 of the forecast, model's comparing fairly well. What's unique though is 5 days out, the model predicts the bloom will move out here into the Central Basin towards Ontario, which is pretty well matched by the observation. So this is the kind of stuff we're always looking for. Are we accurately forecasting where this stuff goes, or do we need to retool the models and get better at it? Now finally, I'll end with a little touch on how this also relates to things like hypoxia. So hypoxia just means low oxygen water. So if you've heard the Lake Erie dead zone, right? The two big ones are probably Gulf of Mexico and Lake Erie dead zones. That just means low oxygen water, typically on the bottom of the lake. This impacts fish, so fish can't survive in it, so they try to avoid that dead zone. But it also impacts drinking water. When that low oxygen water hits the water intakes, they have to treat differently, right? So it actually affects the way they treat the water. So they need that information about, is this going to come, and do we have to change our process? So this is an example of the size of that dead zone in 2012. I think it was covered 35% of Lake Erie in 2012. It's varied over many years. But somewhere between 20 and 35% coverage of Lake Erie each summer. Depends on a number of factors. Some is the algal bloom, the nutrients we're putting into the system, but it's also things like rain, how much rain is coming into the lake as well. This is, if you're like me, this is a little bit tough to grasp the scale of this. And if you plot this over, say, a map of state of Michigan, this dead zone really stretches pretty much from Ann Arbor to Kalamazoo. So it's a massive bloom, or I keep saying bloom, a massive dead zone, right? So if you think, again, from the fish standpoint, that's a massive piece of real estate to avoid because you can't breathe down there. And again, if you're drinking water intakes, that's really on your doorstep for most of the summer. So again, we use the same kind of models, these current forecasting models, to predict not only when that dead zone is going to form, but also how it's going to move around. If you can imagine, just like sloshing in a bathtub, that dead zone, once it forms, moves around in the lake in kind of these oscillating patterns. And every now and then, if the wind blows hard enough, it might hit the shoreline and actually impact a drinking water intake, right? So Cleveland has to deal with this all the time. All summer long, they're kind of on the lookout for low oxygen water. So to help them out, we do a very similar thing, hypoxia forecasting. This is a plot, a rainbow plot of bottom dissolved oxygen, or basically think about it, this is where the dead zone is. Anything in the blue is the dead zone, so this is from this summer. You can see the dead zone pretty much taken over the whole middle of the lake, and at various times impacting the shoreline here, where Avon Lake's water intake is, Mentor, Ashtabula. All those places are where they're watching for that in this case, that blue water to hit. When that blue zone hits, again, they have to change the drinking water treatment process. You can watch it again here. This is in June. You see that bottom water start to become low oxygen in July now. Starts near shore, starts to go offshore. And again, this varies each year depending on environmental conditions. And just like in all these cases, we're comparing to observations. So this is a plot of dissolved oxygen from, I think this is actually the Cleveland intake. So we can see the observations are in black here, the model's in red. So over the course of the summer, oxygen dropping down, down, down. Anything below this gray line is hypoxic, which means they have to change the way they treat the water. You see the model tracks fairly well. Again, not always. It takes a lot of effort, a lot of retooling of these things to get these to be as accurate as they can be. And all that information, just like the currents, gets put on our website. So if you go to GLERL's site, under quick links, we have a special tab for HABs and hypoxia. It shows these two forecasts that I show, as well as a suite of other information, models, and observations, webcams that we have around the Great Lakes. And again, if you have trouble finding this, you can shoot me an email, and I'll point you hopefully in the right direction. And so with that, I will wrap up. I believe we're taking questions, as I mentioned earlier, at the very end. So ignore this question slide, and I'll talk to you in a few minutes.
Well, good evening. It's great to see everybody here. I'm Liz Kirkwood, and it's always a pleasure to speak before League of Women Voter, make a presentation before League of Women Voters. I always enjoy the questions and engagement, and I just want to give special thanks to Dr. Anderson for a really great presentation, and it's I can't express our gratitude to scientists who are working on one of the most complex and important ecosystems here on the planet. I'm going to start our talk off just really noting about the global water crisis. I think living here in the Great Lakes, I can't help but read reports around the world always thinking about water issues. From Syria to the droughts and flooding in California. You may, for example, have read about how Cape Town is on the brink of literally running out of water. The residents are now looking at operating on 13 gallons a day. So these are dramatic days, and I think it was National Geographic said this is all the water that we will ever have, and that's something very, very sobering for us to remember when we think about how extraordinary this ecosystem is, that we've got 20% of the world's fresh surface water, and it really it weighs a heavy responsibility for the 40 million residents who live here in the 8 Great Lakes states and 2 Canadian provinces to figure out how are we going to be stewards of these extraordinary ecosystems. And this is from GLEAM, the Great Lakes Environmental Assessment Mapping Project, that analyzed 22 different challenges from invasive species to climate change, and as you can see, the red areas indicate greater, declining health in those lower lakes, and arguably healthier lake up north. But here are some of the issues. Of course, the dead zone issue that Dr. Anderson just mentioned, and I think what is really interesting to think about with Lake Erie is that in the 50s and the 60s, as he mentioned, we saw these terrible algal blooms. And that was primarily from the phosphates that were directly discharged into Lake Erie and from urban runoff. And with the passage of the Clean Water Act in 1972 and the Great Lakes Water Quality Agreement, because of the regulation of that point source pollution, we saw this incredible revival, and we saw the health of Lake Erie come back. What we are now seeing, though, is the combination of runoff from agricultural pollution and combined CSOs, the combined sewer overflows, that are contributing to the algal blooms. And so we're seeing some of the limitations in our environmental regulations that end up with algal blooms, major American cities without water for several days. We have, those pictures speak for themselves. So at Flow for Love of Water, we are looking at these issues, these very complex systemic issues throughout the Great Lakes, through the lens of what's known as the public trust doctrine, which dates back almost 2,000 years to the Romans, and is something that we kind of all know. It's deep in our DNA, and it says that there are some resources, like water, that belong to all of us. They are our commons. And they are held in trust by, in this country, because it moved from Roman times to England and then to the shores here as colonies. And so when every state joined the Union, and Michigan was 1837, the state of Michigan agreed to be the trustee of the navigable waters in perpetuity for you as citizens, as beneficiaries. So what does that mean? Well, it means, and this is how we come to all these issues, and these are just a couple of programs that we work on that with issues, for example, with Nestle's renewed interest to remove 400 gallons per minute. The question before the DEQ is, will 400 gallons per minute be allowed? Can the ecosystem take that? Will there be harm to these headwater creeks? And our founder, Jim Olson, was the lead attorney in the original litigation against Michigan citizens, where he represented Michigan Citizens for Water Conservation against Nestle. in the Sanctuary Springs area down here. And that was, at that location, identified that working with Dr. Heineman and Dr. Ludington, hydrologist and biologist respectively, that 400 gallons per minute will dry up the headwaters of these very fragile creeks with a cone of depression expanding out. And so a lot of our work is putting together the legal and the scientific case on very important public issues about diversions outside of the Great Lakes Basin. And not surprisingly, this issue with Nestle and the confluence with the Flint and Detroit issues have really come to a head here in the state of Michigan. And at the hearing last April, Nestle is trying to take 2 million gallons of water for $200 a year. Meanwhile, residents in Flint are paying $200 a month. And so the equity issue has been right at the fore. But I want to talk about Line 5 and why this really epitomizes the kind of work that we do, and talks about the importance of why citizens need to be informed about our public waters and to hold our state leaders accountable. And let's see, there we go. And so many Michiganders were not, of course, aware of the Line 5 pipelines that are in the open waters of the Straits of Mackinac. And it wasn't until the 2010 disaster of Enbridge's Line 6B rupture that it took them 17 hours to respond. The National Transportation Safety Board in their report identified, Enbridge as keystone cops, really mishandling this disaster, leading to almost 1 million gallons of the heavy tar sands over a 40-mile stretch, costing about $1.2 billion in cleanup. And before, and that's Line 6B right there. But to understand the story about Line 5, it's really important to kind of just understand where all of this oil is going and is coming from and where it's going. And so there's this is the area of the tar sands up in Alberta. And this is an area about the size of New York State. So imagine New York that has really been kind of excavated, boiled, and shipped. And this is very, thick stuff. And it's in order to transport it economically, it has to be about $90 a barrel. So this is called the Alberta Clipper. It comes down about 1,000 miles into Minnesota, and here in Superior, Wisconsin, this is the beginning of Line 5, and it traverses across the Upper Peninsula, and then, of course, this 5-mile stretch, and then down the Lower Peninsula, and then underneath the St. Clair River. Oh, sorry, and just say one more thing. And so what you can see here is that most of this tar sands that's being refined at refineries around here in the Great Lakes, they're also really destined for export down to the Gulf of Mexico and out to the eastern seaboard. So here's Line 5, closer look. And every day we've got about 23 million gallons of oil going through the Straits of Mackinac. And about 80% of the cargo is light refined oil. So it's not the heavy tar sands that was in Line 6B. At the time in 1953, and this is a view from the North Shore looking down, Lakehead Pipeline Company, now Enbridge, came to the state of Michigan, and they wanted to transport Canadian oil back to Sarnia. So I'll just show you that one more time. And it made sense to, come to the governor and say, we want to build this pipeline. We're coming out of World War II, and this is a time where, they had never built pipelines like this before. And the pipeline is about 30 inches in diameter here on the shore, but when it gets to the straits, it is two 20-inch pipelines, and that's to reduce the pressure. So in order to build these pipelines, what was fundamental to the construction was that the state of Michigan grant permission to Enbridge to build these pipelines. And this easement is held in public trust. And so that what that means is that, at that time, the state should have evaluated whether or not this private interest would have a substantial likelihood of harming the public waters. But of course, in 1953, it was a very different it was a different time. And even the Attorney General for the state of Michigan has said you'd never build a pipeline like this today. And so in 2012, a woman named Beth Wallace from the National Wildlife Federation, who lived in the Kalamazoo area, she and Jeff Alexander authored Sunken Hazard Report and really raised and elevated this issue in a lot of people's minds. National Wildlife Federation then sent down a diver to see this pipeline and, found all sorts of biofouling from invasive mussels that entered into our ecosystem after the construction of this pipeline because, as you know, the seaway was opened in 1959. So initially, this is post 2014. The governor created an executive order and put together a pipeline task force. What are we going to do with this pipeline? And the 4 recommendations that came out were, first of all, to ban heavy tar sands in the line. The second was to create an independent risk analysis. The third was to create an independent alternatives analysis. And then finally, number 4 was just to gain more information from Enbridge. Because even though the state was the trustee, they had literally just sort of forgotten about this pipeline for almost 60 years. And as this report came out, the Attorney General said that the days of this pipeline were numbered. After, and I was going to say, and after that report was done, then the governor created this advisory board. And they've been working on developing both the risk and the alternatives report for over 2 years. And as many of you know, the risk report, both of these reports were due this summer. The risk report was tainted because of conflict of interest, and the alternative report just came out in December. But I have a lot more of the story to tell you that I think that is important just as background. So FLOW and many other organizations came together because we felt that it was very important to hold the state accountable, identify known easement violations related to the integrity of the pipeline and its location in one of the worst possible places in the Great Lakes. And This map over here in the right corner identifies over 70 communities that have either asked for the decommissioning or partial closure of Line 5. All of the 12 tribes in the state of Michigan have, and there are many businesses, including the Great Lakes Business Network, that have come out. Larry Bell is, well known. I don't have to talk about this. I have the expert who did this report right here. This is the 2016 oil spill simulation, examining 860 different potential scenarios that concluded that over 720 miles of coastline were vulnerable, exposing hundreds of thousands of people's drinking water at risk. Remember the winter of 2013 and 2014? Well, the Straits of Mackinac were covered in 6 feet of ice. And the technology and the ability to clean up during a winter potential rupture is really quite limited. And one more thing I'll just say about this is that according to the U.S. Coast Guard, recovery of 40% of the oil is deemed a real success. So it is enormously complex in this ecosystem, as we've seen. We also know about Enbridge's track record. Part of doing business is, pipelines are the safest mode of transporting oil over rail, over truck. However, pipelines rupture, and it's part of the cost of doing business. Back in 2015, we worked with a number of technical experts to think about how would you problem solve this? How would you decommission this pipeline? And what we found is that this pipeline was only providing about 5% of the oil to Michigan, and the rest was going to Canada. And moreover, that there was capacity in existing pipelines going around the Great Lakes. Following the Kalamazoo disaster, a portion of Line 6B was expanded from 400,000 barrels per day up to 800. So from Chicago up to about Stockbridge, that doubled in capacity. And so that there are options here. In terms of economics, Enbridge, the property and sales tax is about $22 million a year, which is significant to a lot of the communities up north. But in terms of what the Great Lakes are in terms of a regional economic engine, it's about $22 billion just in tourism alone. And also, I would like to say that the tribal fishing is the heart and center and the soul of their treaty rights, their fishing rights. About 60% of the whitefish are harvested from here. This is I'm getting the sign here. 5 minutes. This is a long, complicated story. The latest information is that we now know that Enbridge has been untruthful to the public and to both the state and federal agencies for over 3 years. One of the fundamental problems is because of these wild currents, there's a lot of erosion on the lake bed. And so since 2002, Enbridge has been trying to stabilize this pipeline with anchoring structures that actually have led to these pipeline coating gaps. And that's what these pictures are. So lots of words. Sorry about that. There's just too much to say about this. But very quickly, where we are now is we have an alternatives analysis that never examined the existing infrastructure around the pipeline. It also favored a tunnel option, and there's a lot of information here. But one thing that I think is important to remember is that the alternatives analysis made it clear that decommissioning is possible. The issue of addressing propane in the UP can be addressed with perhaps building a 4-inch pipeline from Superior, Wisconsin to Rapid River. You could also address the oil in northern lower Michigan by building another 8-inch pipeline down to Marathon. The system is flexible, and if we are able to put a plan and analyze these issues, we can get there faster. Unfortunately, we've had a lot of delays, and most recently, the governor, right after Thanksgiving, entered into a deal with Enbridge to only study the tunnel option, and that, of course, we believe is a real problem. And this is what I was just talking about. Our focus now is really how do we demonstrate to the candidates, to the public, about a real plan that protects Michigan citizens, businesses, tribes, and how do we protect the paramount interests of the Great Lakes. There has been, I will just say, there's been tremendous bipartisan support to shut this pipeline down, and 2018 is going to be a very, very critical year on this issue, and there's nothing more precious than these lakes, so I will stop there. Thank you.
This program was recorded on January 23rd, 2018 at the Ann Arbor District Library.